So in this video we're going to look at using the sum and difference identities for cosine, the ones that we derived in the previous video. So these are just going to be basic mechanical style problems. So this first one says find the exact value for cosine of pi over 6 minus pi over 4. And what we would want to notice is if we try to write this as a single angle, right, we would need to find a common denominator. And the common denominator would be a 12, so we would need to multiply this by 3 over 3 and this by 2 over 2, and we'd wind up getting the cosine of 2 pi minus 3 pi, which would be negative pi over 12. And if we're after the exact value, the issue is that the denominator of 12 doesn't correspond to any of the denominators that we have for our special angles. Our special angles have denominators like 2, pi over 2, pi over 4, pi over 3, pi over 6. And we wouldn't be able to get the exact value from what we have here because it doesn't correspond to a special angle. So writing the angle as the sum or difference of two special angles allows us to use the trig identity, the difference identity for cosine, to get the exact answer. So the difference identity has cosine, the product of the cosines, and it's a minus, so it's going to be a plus, and then it's going to be the product of the sines, and then we just lever in our angles. It's cosine of pi over 6, cosine of pi over 4, sine of pi over 6, and then this should be sine of pi over 4. And then we just need to remember where these are located on the unit circle so that we can get the correct ordered pairs. So our pi over 6 is going to be that 30-degree angle with ordered pair root 3 over 2 comma 1/2. So that's going to be a 30-degree angle, or pi over 6 radians, and our pi over 4 is our 45-degree angle right here. It's 45 degrees, or pi over 4 radians, and it has the ordered pair root 2 over 2 comma root 2 over 2. And so we just lever in the cosine and sine values, understanding that the cosine and sine are represented by the x and y ordered pairs on the unit circle. So the cosine of pi over 6 is going to be root 3 over 2. And the cosine of pi over 4 is going to be root 2 over 2. Plus the sine of pi over 6 is going to be the y-coordinate for the pi over 6 radians, which is 1/2. And the sine of pi over 4 is also going to be root 2 over 2. And now we can combine things with the common denominator of 4. And I would suggest factoring the pi over 2 off, which would leave a root 3 plus 1 as the exact answer. So here we have the cosine of 105 degrees, and the goal when you get something that looks like this is to try to write it as a sum or difference of two special angles, or angles for which we know the special angle in quadrant 1. So 105 degrees, what we want to notice is that 105 degrees is just 60 degrees plus 45 degrees. And I actually have the cosine of 7 pi over 12 here as well. And it looks initially like it's two distinct problems, but it actually isn't, because if we take 7 pi over 12 radians, we convert it to degrees by multiplying 180 degrees over pi radians, and the radians cancel, the pi cancels, and we get 7 times 180 over 12, which is actually going to simplify to 105 degrees. So we actually have the same angle, one written in degrees, one written in radians. So I'm going to take care of this first, and then we'll step over and take care of this one, understanding that they are the same problem. So this is cosine of 105 degrees. which is equal to the cosine of 60 degrees plus 45 degrees, which then lets us use the sum identity for the cosine function to rewrite this as cosine, the product of the cosines, and it's plus, so the identity is going to have the minus in it. It's going to be the product of the sines, and we're going to get 60 degrees, 45 degrees. I guess that was bad. Thinking. And it's a minus, so it's going to be sine of 60 degrees and sine of 45 degrees. And then it's just a matter again of understanding where you are on the unit circle. So for 60 degrees on the unit circle, 60 degrees we're up here, and the x-coordinate will be a half because the base of that triangle is not as wide as the height, so the larger number goes with the height, so the root 3 over 2. And 45 degrees, we just saw that on the previous slide that corresponds to the xy ordered pair root 2 over 2 comma root 2 over 2. So we would just step in and make our substitutions. The cosine of 60 degrees is the x-coordinate for a 60-degree angle, so it's just a half times the cosine is the x-coordinate for the 45-degree angle on the unit circle, so root 2 over 2. And we have a minus, and we have, making me want to double check there, yep, I did it right. And the sine of 60 degrees is going to be the y-coordinate for the 60-degree angle, so root 3 over 2 times root 2 over 2. And I could write it like this, square root of 2 times 1 minus the square root of 3 all over 4. Or we could write it, or I could have chose to factor the root 2 over 2 out as well, which would give us 1/2 minus the square root of 3 over 2, which we could then just write all over 2. Not doing a good job there, am I? Either of those two forms are kind of nice. So if we were working with the cosine function, the idea is we need to rewrite 7 pi over 12 in terms of special angles. And what we want to recognize is, let's ignore the pi for a minute. We're just looking at different ways of making the 7 in the numerator. I could do 1 plus 6 over 12. We could have 2 plus 5 over 12. We could have 3 plus 4 over 12, and then it would go 4 plus 3, and we would just be counting backwards. So these are the different ways to, using addition, make a 7 pi over 12. But what we want is ones that will reduce with the 12 to give us special angles. So for example, 2 over 12 would give us a 6 in the denominator, but 5 over 12 wouldn't reduce. We'd be stuck with the 12. So this one looks useful because 3 goes into 12 4 times, 4 goes into 12 3 times, and those correspond to special angle denominators, right? Our denominators are pi over 2, pi over 3, pi over 6, pi over 4. The trick is to get denominators that correspond to special angles. So what we want to do is rewrite the 7 pi over 12 using a 3 and a 4. So we go cosine of 7 pi over 12 is just the same as the cosine of, and we would get 4 pi over 12 plus 3 pi over 12. Again, choosing the 4 and the 3 so that they reduce with the 12. 4 goes into 12 3 times, pi over 3 plus 3 goes into 12 4 times, so that we get special angle denominators showing up. And then we can use our identity to go cosine of pi over 3, cosine of pi over 4, minus cosine pi over 3, cosine pi over 4. And once we get here, we recognize that 60 degrees is the pi over 3 and 45 degrees is the pi over 4. So we would wind up doing this work again the rest of the way down. So we're not going to do that. We're just going to stop here and say it's the same now as what we did right here, because those problems are really the same. So here's one, And the only point of this is just to recognize that you can go backwards. So in the previous examples, we went from the cosine of the sum or difference to expanding it into this form, but we can also compact in the other direction. I recognize I have the product of cosines minus the product of sines, and the angles are matched up. So we have matching angles there, we have matching angles here. So we can compact this. We can say, hey, the cosine of the stuff, 7 pi over 36 cosine of 5 pi over 36 minus the sine. And I wanted to be lazy and not rewrite it, but I think in general on homework the expectation is that you rewrite the problem. So I'm going to be good and do that. So I see the minus, so I'm going to recognize that I get the cosine of a sum of two angles, and those two angles are 7 pi over 36 plus 5 pi over 36, and that's going to give us cosine of 12 pi over 36, which is just cosine of pi over 3, which is the 60-degree angle. So again, we want to recognize that pi over 3 is that 60-degree angle corresponding to 1/2 and root 3 over 2. So the cosine is just the x-coordinate, so it's 1/2. So final example says find the sine of alpha. For sine of alpha equaling 112 over 113 with terminal side in quadrant 2, and the secant of beta equaling negative 89 over 39 with terminal side also in quadrant 2. Find the cosine of alpha minus beta. So we want to use the fact that we know that the cosine of alpha minus beta by our difference identity for the cosine function is just the cosine of alpha times the cosine of beta, and it's minus, so we're going to get a plus sine alpha sine beta. And we need to remember that the cosine of an angle, of any angle, is defined to be x over the radius if we're working in the xy plane, and the sine of an angle is defined to be y over the radius if we're working in the xy plane. So we want to come up with our xy coordinates using the information that's been provided. So working first with angle alpha, we want to think about what we've been given. We were told that the sine of alpha, which we know is equal to y over r, we know that that is 112 over 113, which tells us that we don't know what x is, but we do know that y is equal to the numerator 112, and we know that r is equal to 113. And what we want to remember is that we are going to be on some circle of radius 113. So we're going to be on a circle of radius 113, and we don't know the x-coordinate, but we do know the y-coordinate. And so what we do is use the Pythagorean theorem to calculate the x-coordinate, because the absolute value of x is going to be the width of this triangle, which is going to be 112 high and have a hypotenuse of 113. So to calculate x, we go x squared plus 112 squared equals 113 squared, which means x squared is going to equal 113 squared minus 112 squared. And because we're in quadrant 2, x is going to be negative, so when we take the square root of both sides, we are going to want the negative square root of this stuff. And when we crunch this in the calculator, we get a negative 15 as our x coordinate. And then we use this information to do the same thing. We step over and we say, what do we know for our angle beta? Well, for our angle beta, we know we have the secant, and we remember that the secant, should give myself a little room here, the secant of an angle is defined to be r over x, because it's the reciprocal of the cosine function, and that tells us that r is 89, and x is negative 39. We're in quadrant 2. R is always positive. The x coordinate must be negative. And we don't know what y is. We do know what r is. R is the 89. So we extract that information from the ratio, and then we recognize that, hey, we're on a circle in quadrant 2. We have a radius of 89. We know the x coordinate is negative 39. We need to calculate y, which is just the height. So again, we use the Pythagorean theorem. We say, hey, negative 39 squared plus y squared is going to equal 89 squared, which means that y squared is just going to be 89 squared minus 39 squared, because squaring the negative will kill it. So y is going to be the positive square root, because in quadrant 2 y is positive. Y is going to be the positive square root. And if we crunch that out in the calculator, we get y is equal to 80, and we pop that in here. And once we have this information for angle beta and this information for angle alpha, we're ready to get our exact answer, because the cosine of alpha is just going to be the x coordinate, negative 15, over the radius. And we have to do x over r. We can't just do the x coordinate because we're not on the unit circle. And then the cosine of beta is going to be its x coordinate, negative 39, over r, which is 89. Plus, we get sine of alpha. So we go over to alpha, we know we get y coordinate over r, so 112 over r113. And sine of beta is going to be the y coordinate, which is 80, over r, which is 89. And crunching this all out in a calculator, because I was too lazy to do it in my head or on paper, I got 9545 over 10057, which didn't reduce, didn't have any common factors. So this is the exact answer.